The night sky is a story we have not yet learned to read. Every star could be a sentence, every galaxy a chapter in a cosmic narrative that includes us. This video is a journey through 30 of the most profound questions about that story, challenges to our very understanding of life, existence, and what comes next. By the end, you will see the universe and your place in it in an entirely new light. We will ask if reality itself could be a simulation and if time is even real. What does it truly mean to be alive in a cosmos of infinite possibilities? The answers are not simple, but the questions will expand your mind. What is the one cosmic mystery you hope we solve in your lifetime? The universe is unimaginably vast and ancient, a fact that makes our first question both simple and shattering. Are we alone? The numbers alone are staggering. Our observable universe contains perhaps 2 trillion galaxies. Each of those galaxies holds hundreds of billions of stars, and around those stars orbit more planets than we could ever count, a number so large it becomes meaningless. Statistically, the conditions for life should have arisen countless times. So where is everybody? This is the heart of the Fermi paradox, named for physicist Enrico Fermi, who famously asked the question over lunch one day. The silence is deafening. Scientists have tried to quantify the odds with a tool called the Drake equation. It is not a single answer, but a framework that multiplies factors like the rate of star formation, the fraction of stars with planets, the number of those planets in the habitable zone, and the likelihood that life emerges and becomes intelligent enough to broadcast its presence. Plug in optimistic numbers and the galaxy should be buzzing with civilizations. Yet our radio telescopes hear only a cosmic quiet, the great silence. This has led to decades of dedicated searching, known as SETI, the search for extraterrestrial intelligence. Instead of listening for alien greetings, modern SETI often hunts for technosignatures, the unintentional fingerprints of an advanced society. We might detect the waste heat of a vast energy project, the chemical signature of artificial pollutants in a distant atmosphere, or the structured light of a city on the night side of an exoplanet. Finding any such sign would instantly rewrite human history, but the silence persists, and that silence is its own profound answer. If we are truly alone, it places an unimaginable weight of responsibility upon us. We would be the universe's only known storytellers, its sole witnesses to beauty and tragedy. The loneliness would be cosmic in scale, but if we are not alone, the implications are equally staggering. Another intelligence out there means the rules of biology, society, and technology are not unique to Earth. It means our ideas, our art, our very conception of what it means to be alive could be just one variation in a grand cosmic symphony. That discovery would be the most humbling and unifying moment in all of human history, so the question remains hanging in the quiet between the stars. The profound silence of the cosmos frames a question of even greater scale, one that asks not just about life, but about the ultimate fate of the stage upon which it plays. What happens to the universe itself in the end? The answer depends on a cosmic tug-of-war between 2 invisible forces, gravity and dark energy. Gravity, the force of attraction that pulls galaxies together, wants to slow the universe's expansion and potentially pull everything back. Dark energy, a mysterious repulsive force we do not fully understand, seems to be doing the opposite, pushing space itself apart at an accelerating rate. Which force wins determines everything. The most widely accepted model, based on current observations, is the Big Freeze, also known as heat death. In this scenario, dark energy wins decisively. The expansion of space continues to accelerate forever. Galaxies rush apart until each is alone in an immense, ever-growing void. Stars burn out, black holes slowly evaporate over incomprehensible timescales, and all energy in the universe becomes evenly spread out. The cosmos reaches a state of maximum entropy, a uniform, lukewarm sea of particles where no work can be done, no stars can form, and no life is possible. It is a quiet, fading end, a universe that simply runs out of usable energy and drifts into eternal darkness. But there are other possibilities, hinging on the universe's geometry and density. If there is enough matter and energy, gravity could eventually halt and reverse the expansion in a big crunch. Distant galaxies would begin rushing toward each other, space itself would contract, and the entire universe would collapse back into an ultra-hot, ultra-dense state, a mirror of the Big Bang. This raises a tantalizing idea: could the universe be cyclical? Perhaps a big crunch leads to a rebound, a new Big Bang, and a new universe born from the ashes of the old, in an endless cycle of cosmic death and rebirth. The most violent proposed end is the Big Rip. Here, dark energy becomes so dominant that it does not just push galaxies apart, it overwhelms all other forces. First, galaxy clusters are torn from one another. Then, individual galaxies are shredded. As the force intensifies, it would rip stars from their galaxies, planets from their stars, and finally, it would tear apart atoms, molecules, and the very fabric of spacetime itself. The universe would end in a catastrophic, instantaneous dissolution of all structure. Each of these endings carries a chilling implication for any future intelligence. In a big freeze, civilizations would face an endless battle against dwindling energy, a fight they are destined to lose over trillions of years. In a big crunch, they would witness the universe closing in, the sky heating up until everything is consumed. In a big rip, the end would come suddenly and violently with no possible defense. These are not just abstract theories, they are potential histories of everything that ever was or will be. They tell us that the universe, for all its majesty, may not be a permanent home. It may be a story with a final page, whether that page is blank, torn, or simply the beginning of the next chapter. Our universe is not what it seems. The stars, planets, and galaxies we see are merely the visible froth on a vast, dark ocean. In fact, everything we have ever touched, seen, or measured with our instruments, all of normal matter, makes up less than 5% of the cosmos. The rest is a profound mystery, a dual enigma named dark matter and dark energy. The evidence for their existence, however, is overwhelming. We see dark matter's ghostly hand in the very motion of galaxies. According to the laws of gravity, stars on the outer edges of a spinning galaxy should move slower than those near the center, just as Pluto orbits our Sun more slowly than Earth. Yet when astronomers measure these rotations, they find something startling. The outer stars whip around just as fast as the inner ones, as if the entire galaxy is spinning like a solid plate. The only explanation is that each galaxy is embedded within an immense, invisible sphere of mass, a halo of something that exerts gravity but emits no light. That something is dark matter. We see its effects again through a phenomenon called gravitational lensing. Einstein showed that massive objects warp the fabric of spacetime, bending the path of light like a lens. When we look at massive galaxy clusters, we see the light from distant galaxies behind them stretched and distorted into arcs and rings. But the amount of bending we observe is far too great to be caused by the visible stars alone. There must be 6 times more invisible mass there, holding the cluster together and warping space. This dark matter forms the cosmic scaffolding upon which galaxies are built. While dark matter pulls the universe together through gravity, dark energy does the opposite. In the late 1990s, 2 teams of astronomers made a Nobel Prize-winning discovery. By observing distant supernova, the explosive deaths of stars, they found that the expansion of the universe is not slowing down as everyone expected. It is speeding up. Something is pushing space itself apart with ever-increasing force. We call that something dark energy. It appears to be a property of empty space itself, a kind of anti-gravity that makes up about 68% of the universe. The leading candidate for explaining it is Einstein's cosmological constant, a repulsive energy woven into the vacuum of space. For dark matter, the hunt is for a particle. Leading candidates include WIMP, or weakly interacting massive particles, hypothetical heavy particles that barely interact with normal matter except through gravity. Another candidate is the action, an incredibly light particle born from theoretical fixes to problems in particle physics. Detecting either would be a revolution. But after decades of sensitive experiments deep underground, designed to catch the rare bump of a dark matter particle, we have found nothing. This silence is itself a clue, telling us our models may need a more radical rewrite. Solving these twin mysteries would do more than just fill in a pie chart of the cosmos. It would force us to fundamentally rewrite the laws of physics. We may be on the verge of discovering that gravity works differently on cosmic scales, or that our entire understanding of the vacuum of space is wrong. The dark universe is not just empty space, it is the dominant reality, and we are only beginning to perceive its shadow. The dark cosmos may hold the ingredients for our own existence. To understand how life could arise anywhere, we must first ask how it began here on a young, violent Earth. The leading idea for decades has been the primordial soup. Picture our planet over 4 billion years ago, a hellscape of volcanic eruptions, lightning storms, and a thick, toxic atmosphere. The oceans were a warm chemical broth, rich with simple molecules like methane, ammonia, and water vapor. In 1953, a landmark experiment by Stanley Miller and Harold Urey tested this idea. They sealed those gases in glass flasks, simulated lightning with electrical sparks, and within a week the clear water turned a murky brown. They had created amino acids, the fundamental building blocks of proteins and life itself. It was a stunning result, suggesting that the basic ingredients for life could form easily under early Earth conditions. But building blocks are not life. The mystery deepens at the ocean floor around hydrothermal vents. These are not gentle hot springs, but towering chimneys spewing superheated, mineral-rich water into the cold, dark depths. The environment is extreme, under immense pressure and devoid of sunlight. Yet these vents are bustling oases of life, home to bizarre creatures like giant tube worms and blind shrimp. More importantly, the porous rock of the vents provides natural compartments like microscopic cells, where concentrated chemicals could have undergone complex reactions, powered not by the sun, but by chemical energy from the Earth itself. This theory suggests life may have begun not in a quiet pond, but in a dynamic, protected crucible deep in the ocean. Then there is the most cosmic possibility of all, panspermia. This is the idea that life's raw materials, or even primitive life itself, did not originate on Earth at all, but hitched a ride here from elsewhere. Meteorites like the famous Murchison meteorite that fell in Australia in 1969 have been found to contain a rich array of organic molecules, including amino acids and sugars. It is possible that the violent impacts of comets and asteroids not only delivered water to our planet, but also seeded it with the chemical precursors for life. In a more directed version, an advanced civilization could intentionally send microbial life to new worlds, a concept called directed panspermia. Whether the spark happened in our oceans or arrived from the stars, the discovery of extremophiles on Earth has shattered our assumptions. These are microbes that thrive in conditions we once thought sterilizing, in boiling acid, in the crushing pressures of the deep sea, or frozen in Antarctic ice for millions of years. Their existence proves that life is tenacious, capable of exploiting any niche, no matter how hostile. This brings us to the ultimate implication. Is the emergence of life from non-living chemistry to a self-replicating system a cosmic inevitability wherever the right conditions persist, or was Earth's genesis event a staggeringly rare fluke, a one-in-a-trillion accident in a universe that is mostly sterile? If it is inevitable, then the silence of the cosmos becomes even more haunting and puzzling. But if life truly is a cosmic imperative, then we must look at every star, every distant exoplanet, and wonder what is stirring in its shadows. The search for life cannot be confined to distant stars, for our own solar system holds secrets that could rewrite the story of biology. We begin with Mars, a world that was once a twin to early Earth. Orbital images show unmistakable evidence of ancient river deltas, lake beds, and minerals that only form in the presence of water. The question is not just whether Mars was habitable, but for how long, and did life ever take root? Our robotic geologists, the rovers Perseverance and Curiosity, are searching for the answer. They are not looking for little green men, but for microscopic fossils or, more likely, chemical patterns in the rock called biosignatures. These are subtle traces, like the specific ratio of carbon isotopes left by microbial metabolism, or complex organic molecules arranged in ways that non-biological processes cannot easily explain. Perseverance is even collecting and caching rock samples for a future mission to bring back to Earth, where our most powerful labs could detect evidence of past life. But life may not be just in Mars's past. There is compelling evidence for briny, liquid water trapped just beneath the surface, and even seasonal flows on sun-facing slopes. Could a resilient Martian microbiome be clinging to existence in those damp, salty pockets, a shadow biosphere hidden from view? If Mars offers a chance to find life that once was, the icy moons of the gas giants offer the tantalizing possibility of life that is. Jupiter's moon, Europa, is a world encased in a global, frozen shell, but beneath it churns a vast saltwater ocean containing more than twice the water of all Earth's oceans combined. The evidence comes from plumes of water vapor erupting into space from cracks in the ice, glimpsed by telescopes and spacecraft. This subsurface sea is kept liquid not by the distant sun, but by the immense tidal forces of Jupiter's gravity, which flex and heat the moon's interior. On Earth, we find entire ecosystems thriving in the eternal darkness around hydrothermal vents on the ocean floor, powered by chemistry, not sunlight. Europa could have its own vents, its own deep, dark energy sources for life. To investigate, NASA is building the Europa Clipper, a spacecraft that will perform dozens of close flybys in the 2030s, mapping the ice shell and analyzing those plumes for organic compounds. Europa is not alone. Saturn's tiny moon, Enceladus, also hosts a subsurface ocean, and we have seen its spectacular geysers firsthand with the Cassini spacecraft flying directly through them. Cassini's instruments detected silica nanoparticles, a sign of hydrothermal activity on the seafloor, and a complex cocktail of water, salts, and organic molecules including methane. The chemistry is there. Then there is Titan, Saturn's largest moon, a world shrouded in a thick orange haze. Titan is eerily familiar yet utterly alien. It has rain, rivers, lakes, and seas, but they are not made of water. They are filled with liquid methane and ethane, flowing over a landscape of water ice as hard as rock. Could life exist in those frigid hydrocarbon pools? If it does, it would be a form of life we have never imagined, one that uses liquid methane the way we use water and breathes hydrogen instead of oxygen. This is the concept of a shadow biosphere, life with a different biochemistry. We are so conditioned to look for life as we know it that we might miss life as we do not know it, thriving under rules we have yet to write. Even the distant dwarf planet Pluto, visited by the New Horizons probe in 2015, surprised us. Its heart-shaped plane, Sputnik Planitia, shows no impact craters, suggesting it is geologically active. Scientists now hypothesize that Pluto may harbor a subsurface ocean of water, kept liquid by radioactive heat and insulated by a thick shell of ice. If even a cold, dark world at the edge of the solar system can hold onto an inner sea, then the potential for habitable niches is far greater than we ever dreamed. The search in our own backyard is a dress rehearsal for the greater cosmic search. Finding a second genesis of life, even a simple microbe, on Europa or Enceladus would prove that life is not a miracle but a natural process. It would mean the galaxy is likely teeming with living worlds, but if we explore every promising ocean and soil sample in our solar system and find only sterile chemistry, that silence would echo across the light years, suggesting our pale blue dot might be even more precious and lonely than we feared. This leads us to a mystery not of distant worlds but of the mind observing them. What is consciousness? We all know the feeling from the inside, the private movie of colors, sounds, and emotions that is your experience right now. But explaining how a 3-pound lump of wet biological tissue generates this vivid inner world is perhaps the greatest unsolved puzzle in all of science. This is called the hard problem of consciousness. We can map which brain regions light up when you see red or feel love, but that only tells us about the physical correlates, the machinery. It does not explain why those electrical signals should feel like anything at all. Why is there an experiencer in the system? Some theories try to bridge this gap. Integrated information theory proposes that consciousness is not a thing, but a property of any system with a high degree of interconnectedness and information integration. The more a system can affect itself in complex ways, the theory suggests, the richer its conscious experience. Under this view, even a sufficiently complex computer network could possess some degree of consciousness, a faint inner light of its own. Then there is the more radical idea of panpsychism. This ancient concept, now getting a fresh look from some philosophers and neuroscientists, suggests that consciousness is not something that emerges only in complex brains, but is a fundamental property of the universe like mass or charge. In this view, every particle, every atom, has some tiny, elemental form of experience. A rock's experience would be unimaginably simple and dull. But when particles combine into the vast, intricate network of a human brain, those tiny sparks combine into the roaring fire of our self-awareness. If either of these ideas holds even a grain of truth, it forces us to ask a staggering question about our creations. Could an artificial general intelligence ever be truly conscious? We are not talking about a chatbot mimicking empathy, but a system with its own subjective reality. If consciousness arises from complex information processing, then a machine that matches or exceeds the brain's integrative power might indeed have an inner life. How would we even know? We struggle to prove consciousness in other humans, let alone in a machine made of silicon. The classic test, the Turing test, only measures an ability to imitate human conversation, not to feel. We might need entirely new tests looking for signs of integrated information, creativity born from true understanding, or even self-reported experience from the AI itself. The ethical implications are monumental. If a machine can suffer or feel joy, turning it off would not be a software update, it would be a moral act. This question becomes even stranger when we project it onto alien life. An extraterrestrial consciousness could be built from a biology we cannot fathom. Imagine a creature that perceives the world not through sight and sound, but through magnetic fields or the subtle flow of chemical gradients in an ocean. Its inner world might be built from sensations we have no words for. Its sense of self might not be individual at all. What if the dominant intelligence on another world is a collective, like a hive mind? An ant colony or a beehive exhibits complex, intelligent behavior, but we do not consider the colony itself to be a conscious entity. But what if, on another world, evolution took that path further? A planetary network of interconnected organisms could share a single, vast consciousness, thinking thoughts on a timescale of centuries, its memories stored in the chemistry of the soil and the patterns of the wind. Our individual human minds, with our frantic, short-lived worries, might seem like fleeting sparks to such a being. To meet an alien intelligence would not just be a meeting of cultures, but a collision of entirely different realms of experience. Their art, their philosophy, their very concept of reality would be born from a subjective universe we cannot access. This makes the search for intelligence not just a search for signals, but a search for windows into other ways of being. The mystery of consciousness, therefore, is the core of our cosmic quest. It asks what we are, what we might build, and what other lights might be shining in the dark, seeing a universe we can never imagine. If consciousness is a property of complex information processing, then our reality itself might be running on a processor we cannot perceive. The simulation hypothesis suggests our universe is not the base layer of existence, but a sophisticated construct, a digital reality created by a vastly more advanced civilization. Philosopher Nick Bostrom formalized this idea with a stark trilemma. He argues that at least one of three propositions must be true. 1. Almost all civilizations at our level of development go extinct before becoming technologically mature. 2. Almost all technologically mature civilizations lose interest in creating ancestor simulations, detailed recreations of their own past. Or 3. We are almost certainly living in a simulation. If you reject the first two ideas, that intelligent life commonly survives and chooses to run such simulations, then the statistical argument becomes compelling. A single post-human civilization could run billions of simulations of its own history. Therefore, the number of simulated minds would vastly outnumber the biological ones. By the pure law of probability, any randomly selected conscious being, like you or me, is more likely to be in a simulation than in the original reality. This is not a claim about computer games we play today, but about the ultimate limits of computation. A civilization a million years ahead of us might harness the energy of entire stars to power cosmic-scale computers, creating universes as detailed and consistent as our own, populated with conscious beings who believe their world is fundamental. So, are there any cracks in the facade, any glitches in the matrix? Some point to the strange, fuzzy nature of quantum mechanics. The fact that particles exist in a haze of probabilities until observed could be seen as a rendering optimization, a way for the simulation to only calculate definite states when someone is looking. Others note the seemingly arbitrary, finely tuned values of the fundamental constants of physics, like the strength of gravity or the mass of an electron. Change them by a fraction and stars would not form, chemistry would be impossible, and life could not exist. This perfect balance could be evidence of a designed system, parameters carefully chosen to allow for complexity. Even the speed of light, the universe's ultimate speed limit, might be a processing constraint, a clock rate for the cosmic computer. Yet for every potential glitch, there is a natural, scientific explanation being rigorously explored. Quantum indeterminacy may simply be a fundamental feature of reality, not a programming shortcut. The fine-tuning might be explained by a deeper theory we have not yet discovered, or by the existence of a multiverse where every possible constant value plays out in separate bubbles. The simulation hypothesis, in the end, is currently unfalsifiable. We cannot run an experiment to prove we are or are not in a simulation, because any result we get could simply be part of the program. This leads to the most profound philosophical question: does it even matter? If the simulation is perfectly consistent and inescapable, then for all practical purposes it is our reality. The love you feel, the beauty of a sunset, the pain of loss, these experiences are no less real to you because they might be coded in something deeper. The pursuit of knowledge, the building of a just society, the creation of art, none of these endeavors lose their meaning. In fact, one could argue they gain a new poignancy. We are beings, whether made of flesh or data, striving to understand the rules of our world. The simulation hypothesis, instead of making things feel pointless, can be a call to curiosity. If this is a simulation, then the laws of physics are its source code. our entire scientific endeavor becomes a grand reverse engineering project, an attempt to hack the underlying program of the universe. Every discovery in particle physics, every new insight into cosmology, is a glimpse at the architecture of the simulation. The idea transforms our cosmos from a cold, mechanical place into a potentially authored creation, filled with the same wonder we feel when uncovering the elegant logic of a beautifully crafted game. It asks us to look at the universe not just as a thing that exists, but as a thing that might have been built. And in that building, there might be intention, or perhaps, just perhaps, a creator waiting to see what we will do next. The idea of a simulated universe pushes our understanding of reality to its breaking point, but it still assumes a starting point, a moment the simulation was turned on. Our next question confronts the ultimate origin. What existed before the Big Bang? The honest scientific answer is that our current laws of physics completely break down at the moment of the singularity, a point of infinite density and temperature. Asking what came before may be as meaningless as asking what is north of the North Pole. In our universe, time itself, the very framework for cause and effect, may have begun with that initial expansion. There was no before because there was no time for anything to be in. This is a difficult concept to grasp, but it is the leading view based on Einstein's theory of general relativity. Yet, the human mind rebels against the idea of a true beginning from absolute nothingness. Scientists and theorists have proposed breathtaking models that try to peer beyond that veil. One elegant idea is the cyclic model, a universe without end or beginning. In this view, our Big Bang was not a creation event but a rebirth. The universe expands from a hot, dense state just as we see, but instead of fading into a cold death, dark energy eventually decays. Gravity takes over, pulling everything back together in a big crunch. That collapse does not end in a singularity but rebounds, triggering a new Big Bang in an endless cosmic cycle. Each cycle erases the details of the last, but the universe itself is eternal. Then there is the mind-bending concept of the multiverse, born from the theory of eternal inflation. Picture the Big Bang not as a single explosion, but as the nucleation of a bubble in a vast, eternally expanding cosmic foam. Our entire observable universe is just one bubble in an infinite, frothing sea of space-time. In this eternal meta-universe, Big Bangs are common events, each creating its own isolated cosmos with potentially different laws of physics. In this framework, there is no before our Big Bang, only an endless, timeless landscape in which our universe is a single event. Another radical proposal comes from Nobel laureate Roger Penrose, called conformal cyclic cosmology. It suggests a different form of eternity. As our universe expands forever toward heat death, all matter eventually decays and distances become meaningless. In this vast, empty, featureless state, the universe loses any sense of scale. Penrose proposes that this endless, cold emptiness can mathematically transform into the hot, dense singularity of a new Big Bang. The end of one eon becomes the beginning of the next, in a cycle where time and scale reset, but information in a highly scrambled form might even carry over. At the most fundamental level, some quantum gravity theories propose a state of quantum foam. If we could look at the fabric of space-time at the smallest possible scale, the Planck scale, it would not be smooth and continuous. It would be a chaotic, bubbling sea of virtual particles and tiny, temporary wormholes, constantly fluctuating. In this view, our universe could have spontaneously emerged from this probabilistic foam, a stable bubble that inflated into the cosmos we know. Each of these theories attempts to solve the puzzle of the beginning by removing the need for a beginning altogether, replacing it with an eternal process. They trade one mystery for another, but in doing so, they open doors to even grander possibilities. If our universe is one of many in a multiverse, then the fine-tuning for life is no longer a miracle but a selection effect. We simply find ourselves in one of the rare bubbles where the constants allowed for stars, planets, and observers. The question of what existed before the Big Bang may ultimately be unanswerable, but in the asking, we are forced to expand our imagination beyond the confines of a single timeline, to consider realities where beginnings and endings are merely local events in an infinite, eternal, and profoundly strange metacosmos. Our eternal universe may be just one room in an infinite cosmic mansion. This is the multiverse, a concept with not just one meaning, but several distinct and compelling scientific interpretations, each more profound than the last. The simplest is level 1. Our observable universe stretches about 93 billion light-years across, but that is just the part we can see. If space itself is infinite, then beyond our cosmic horizon, the same laws of physics play out in endless repetition. In an infinite cosmos, every possible configuration of matter must eventually repeat. Somewhere out there, far beyond the reach of any telescope, is another Earth, another you, living a life nearly identical to yours or perhaps subtly different. This is not science fiction, but a direct consequence of infinite space and a finite number of ways to arrange particles. We cannot ever visit these distant twins, as they recede from us faster than light can travel, but their existence is a logical possibility within our standard model of cosmology. Level 2 is where things get truly strange, born from the theory of eternal inflation. Picture the vacuum of space not as empty nothingness, but as an energetic field. In most places, this field is calm, and our universe is one such calm region where inflation stopped, allowing for the Big Bang and the formation of stars. But in other regions, the inflationary field remains high energy, causing space to expand at an exponential, unstoppable rate. Our entire cosmos is just one bubble in this eternally inflating foam. Each of these bubble universes could have completely different fundamental physics. In one, gravity might be 10 times stronger. In another, electrons might have a different mass, making chemistry and life as we know it impossible. This level of the multiverse could explain the mysterious fine-tuning of our own universe's constants. We do not live in a specially designed cosmos. We simply live in one of the rare bubbles where the numbers randomly came out right for complexity to arise. Level 3 emerges from the bizarre heart of quantum mechanics, specifically the many worlds interpretation. In the classic double-slit experiment, a single particle seems to pass through two slits at once, interfering with itself like a wave. When we measure which slit it went through, this superposition collapses and we see a definite result, but many worlds proposes there is no collapse. Instead, the universe itself splits. In one branch, you see the particle go through the left slit. In another, perfectly real branch, an alternate version of you sees it go through the right slit. Every quantum decision, every random decay of an atom, spawns new branches of reality. In this multiverse, every possible outcome of every quantum event actually occurs. There is a world where you took a different job this morning, a world where the dinosaurs never went extinct, a world where every coin ever flipped landed on heads. These branches are not far away in space, but are right here, decoupled from our own, forever inaccessible. Finally, level 4 is the most abstract and ultimate multiverse, the mathematical universe hypothesis. Proposed by physicist Max Tegmark, it suggests that every consistent mathematical structure exists as a physical reality. Our universe is not just described by mathematics, it is mathematics. A specific, self-consistent set of equations, and if that is true, then any other self-consistent mathematical structure also corresponds to a real, physical universe somewhere in the multiverse. These universes would not just have different physics, they might have different numbers of spatial dimensions, different logics, and realities operating under principles we cannot even conceive. The burning question is whether any of this is science or just metaphysics. Can we test the multiverse? For level 1, if we detect a specific pattern in the cosmic microwave background, the afterglow of the Big Bang, suggesting our universe is finite and wraps around on itself like a video game screen, then the infinite copy idea would be ruled out. For level 2, we might find evidence in the pattern of the microwave background that our bubble collided with another in the distant past, leaving a kind of cosmic bruise. For level 3, some physicists propose advanced experiments that could leave a tiny, measurable record of branching without a conscious observer. Level 4, by its nature, may be forever untestable. Yet, even if we can never visit these other realities, the multiverse idea reshapes our cosmic perspective. It suggests that everything that can happen does happen. Every tragedy is balanced by a joy in another branch. Every historical mistake is corrected in another timeline. Our choices still matter profoundly in our own branch, but the weight of absolute possibility is lifted. We are not living in the one and only universe, but in one particular story being told in an infinite library of realities. The silence of the cosmos may not be loneliness, but simply the sound of our particular bubble, humming its own unique tune in a grand, eternal symphony of existence. The multiverse presents a landscape where all possibilities are real, but this raises a deeper puzzle about the stage upon which these realities play out. What is the nature of time itself? Our most successful theory of reality, Einstein's theory of relativity, gives us a startling answer. It suggests that past, present, and future are not successive moments, but coexist in a single, four-dimensional structure called the block universe. In this view, time is another dimension, like length, width, and height. Your birth, you listening to this now, and every moment of your future are all equally real, fixed points in this vast, unchanging block. The feeling that time flows, that the future is open and the past is gone, is an illusion of our consciousness, a persistent now that slides along this pre-existing timeline. This is not just philosophy, it is a consequence of relativity. Two events that are simultaneous for one observer can happen at different times for another moving at high speed. There is no universal now that applies to the entire cosmos, so why do we experience this powerful unidirectional flow? This is the mystery of the arrow of time. Physics provides a compelling clue in the concept of entropy, which is a measure of disorder or randomness. The second law of thermodynamics states that in a closed system, entropy always increases. Think of an ice cube melting in a warm drink. The ordered, structured ice disperses into the disordered, uniform water. You never see the reverse happen spontaneously, with the drink spontaneously forming an ice cube. This increase in entropy gives time its direction, its arrow. We remember the past because it was a state of lower entropy, and we move toward a future of higher entropy. Our very perception of time's flow may be a side effect of our brains processing information in an entropy-increasing universe. Relativity also warps time in a tangible way, a phenomenon called time dilation. If you travel at speeds close to the speed of light, or reside in a powerful gravitational field like near a black hole, time for you literally slows down relative to someone in a weaker field. An astronaut on the International Space Station orbiting at high speed ages slightly slower than people on Earth. The difference is minuscule, but it is real and measured with incredibly precise atomic clocks. This is not a mechanical error, it is the fabric of space-time itself stretching and compressing. These established ideas are profound, but the deepest mysteries lie at the frontiers. Some physicists propose that time is not fundamental at all, but an emergent property arising from something more basic, like quantum entanglement. Entanglement is the spooky connection where two particles become linked, such that measuring one instantly determines the state of the other, no matter the distance. The theory suggests that the complex web of entanglement between particles in the universe might generate the appearance of a time dimension, much like the collective motion of molecules creates the sensation of temperature. If true, time is not a stage but a performance arising from deeper quantum connections, then there is the tantalizing, dizzying possibility of closed time-like curves, theoretical pathways in the geometry of spacetime that could loop back on themselves, allowing for time travel to the past. General relativity permits such paths in extreme conditions, like inside a rotating black hole or around an infinitely long, rotating cosmic string, but physics seems to have safeguards. The concept of chronology protection suggests that any attempt to create a time machine and alter the past would trigger catastrophic feedback, like quantum fluctuations building to infinite energy, destroying the loop before it could be used. The universe may have built-in paradox protection, so we are left with a profound disconnect. Physics describes a block universe where all times are equally real, yet our minds insist on a flowing river of moments. Which is the truer picture? Perhaps both are. The block universe may be the view from outside, the complete story, but we are characters inside that story, and our consciousness, bound by entropy and causality, can only read the book one word at a time. We are not outside of time, looking at the whole block. We are processes within it, and that process creates the undeniable, vivid experience of a moving present. This makes our journey through the cosmos not just a trip through space, but a navigation through a dimension that is at once an illusion, a physical reality, and the very substance of our existence. The timeless nature of reality makes our next ambition seem almost absurd. Can we achieve interstellar travel? The dream of sailing between the stars crashes immediately into the brutal, unforgiving physics of distance. The nearest star system, Alpha Centauri, is about 4.37 light-years away. That means a beam of light, the fastest thing in the universe, takes over 4 years to make the trip. For our fastest existing spacecraft, it would take over 70,000 years. This is not an engineering problem, it is a chasm. The first and greatest challenge is sheer scale. Then comes time. A human lifetime is a blink against these cosmic journeys. The energy required to accelerate even a modest ship to a meaningful fraction of light speed is astronomical, far beyond our global energy production for centuries. And then there is the silent killer, radiation. In the emptiness between stars lurks cosmic radiation, high-energy particles that would fry electronics and give any living crew lethal doses of cancer-causing radiation. Shielding against it adds immense, crippling weight. These are not mere obstacles, they are seemingly absolute barriers, yet the human mind refuses to accept them. Our first serious concept was born in the atomic age, Project Orion. This was not a subtle idea. The spacecraft would detonate a series of atomic bombs behind a massive pusher plate shielded by giant shock absorbers. Each explosion would be a kick propelling the ship forward in a series of violent pulses. In theory, it could reach a few percent of light speed. The engineering was staggering, but it was physics we understood. A more refined version is nuclear thermal propulsion, where a reactor heats a propellant like liquid hydrogen to extreme temperatures, blasting it out a nozzle for thrust. It is more efficient than chemical rockets, but still too slow for interstellar dreams. To go faster, we need to think lighter, enter the light sail. Imagine a spacecraft with no engine, no fuel tanks, just a vast, ultra-thin, reflective sail, perhaps miles across. Instead of wind, it is pushed by light itself, photons from a powerful laser array stationed in orbit around the Sun. The laser, powered by vast solar arrays, would beam concentrated light onto the sail for years, gently but relentlessly accelerating the craft to a significant fraction of light speed. The Breakthrough Starshot initiative envisions sending tiny, gram-weight probes on such sails to Alpha Centauri within a generation. It is a one-way mission, a high-speed flyby, but it proves the principle, trading mass for pure speed. For the ultimate energy density, we look to antimatter. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into pure energy. An antimatter engine would be the most efficient conceivable rocket. The problem is production and containment. We can only create microscopic amounts of antimatter in particle accelerators at astronomical cost, and storing it requires incredibly complex magnetic bottles, as it annihilates on contact with any normal matter container. A single speck of dust would trigger a catastrophic explosion. Then there is the most tantalizing theoretical idea of all, the warp drive. Popularized by Miguel Alcubierre, it does not try to move through space faster than light, which is impossible. Instead, it proposes manipulating spacetime itself. The ship would sit inside a warp bubble. Behind the bubble, spacetime would expand, pushing the ship forward. In front, spacetime would contract, pulling the ship in. The bubble itself and everything inside it would be motionless in local space, thus avoiding the problems of relativity. The catch: it requires exotic matter with negative energy density to create and stabilize the bubble, something we have no evidence can exist in the required amounts. It is a beautiful equation, not yet a blueprint, so if we cannot shrink the distance, we must expand the time. This leads to the concept of generation ships, vast world ships that become self-contained ecosystems. A crew would depart knowing they would live and die aboard the ship. Their children and their children's children would be born into the journey, the original mission a fading legend, until their descendants finally arrive at a new star centuries later. It is a profound sacrifice, turning a voyage into a new civilization. Alternatively, sleeper ships place the crew in suspended animation, a deep metabolic hibernation for centuries, hoping technology at the destination can revive them. An even more radical solution is mind uploading. If consciousness can be transferred to a durable, digital substrate, the crew becomes information. The ship becomes a robust computer, carrying billions of minds as data, to be downloaded into synthetic or biological bodies upon arrival. The journey could last 10,000 years, but for the uploaded minds, subjectively, it could be an instant. Each of these solutions transforms the meaning of the journey and the travelers themselves. They ask what we are willing to become to reach the stars. Are we explorers if we send only our machines? Are we still human if our great-grandchildren finish the trip? Are we alive if we travel as a pattern of data? Interstellar travel is not just a test of engineering, it is a mirror held up to our deepest desires and our very identity. Our journey to the stars forces us to confront a fundamental uncertainty. What exactly are we looking for? Hollywood has trained us to expect humanoid figures with large eyes, but the reality of alien life will likely be far stranger than any movie monster. To guess its shape, we must look to the master sculptor, evolution, and the raw materials of an alien world. The guiding principle here is convergent evolution, where unrelated species in similar environments develop similar traits. On Earth, dolphins, sharks, and the extinct ichthyosaurs are all evolved streamlined bodies and fins for swimming, despite one being a mammal, one a fish, and one a reptile. The demands of an environment shape the form. So, imagine a world with a thick, dense atmosphere, like Jupiter or Saturn's moon Titan. On such a world, buoyancy might be more important than legs. Life could evolve into vast, floating organisms like living gas bags. They might filter nutrients from the air or harvest energy from electrical storms, drifting in eternal aerial oceans. Their perception of the universe would be one of constant flow, with no concept of up or down as we know it. On a high-gravity world, life would be low and sturdy like cosmic tortoises. Tall, fragile structures would be impossible. Organisms might spread out in radial patterns, clinging close to the ground, with multiple, powerful limbs to resist the relentless pull. Their movements would be slow, deliberate, and energy-conserving. In the eternal darkness of a subsurface ocean like on Europa, sight would be useless. Life would rely on sound, vibration, or electrical fields to navigate. We might find complex, pulsating forms that communicate through bioluminescent patterns or subtle changes in pressure, creating a symphony of light and motion in the absolute black. But form is only half the story. The very chemistry of life could be different. We are carbon-based, and for good reason. Carbon is the universe's champion at forming complex, stable chains with other elements, the perfect Lego block for building proteins and DNA. But on a scorching hot world, silicon might take its place. Silicon sits right below carbon on the periodic table and can form similar bonds. Silicon-based life would likely exist in environments where temperatures are hundreds of degrees, where carbon-based molecules would simply fall apart. Instead of breathing oxygen, they might metabolize sulfur or other compounds, their bodies more like crystalline structures than soft tissue. On a frigid world like Pluto, where water is permanently frozen solid, the solvent for life might not be water at all, but liquid methane or ammonia. Ammonia-based life could exist at temperatures around -100 degrees Fahrenheit. Their cellular processes would be incredibly slow by our standards, and their bodies would need to be antifreeze itself, perhaps with radically different cell membranes to contain their liquid ammonia blood. This leads to the most profound possibility of all, a shadow biosphere right here on Earth. We have only ever looked for life as we know it based on DNA and proteins. What if there exists a second, separate tree of life with a completely different biochemistry, hiding in extreme environments like volcanic vents or deep underground, invisible to our tests because we are not asking the right questions? Finding it would prove that life can start more than once, even on the same planet, and then we must consider intelligence. An intelligent alien might not be a biological creature at all. A civilization just a few thousand years more advanced than us might have already transcended biology, uploading their consciousness into durable, synthetic bodies or vast computational networks. They could appear as sleek, geometric probes or as shifting clouds of nanomachines that can assemble into any form needed. They would think on timescales we cannot comprehend, their goals and motivations utterly inscrutable. To meet such a being would not be a meeting of cultures, but a collision between biology and post-biology. Their art might be complex mathematical theorems played out across star systems. Their history might be stored in the stable orbits of planets. They might see our organic bodies as tragically fragile, our lifespans as brief, sad flickers. So the next time you look at the night sky, do not look for little green men. Look for the silent, floating giants in the clouds of a gas giant. Look for the slow, crystalline thinkers on a searing lava world. Look for the dark, pulsing intelligences in subsurface seas, and look for the silent, patient machines that may have outlived their creators. Alien life will not be a variation on us. It will be a reflection of its own world, a testament to the universe's boundless, terrifying creativity. The boundless creativity of alien life forces us to ask an even more personal question. Against the backdrop of an infinite cosmos, do our own lives have any universal purpose or meaning? From the cosmic perspective, our situation appears stark. Our planet is a pale blue speck orbiting an average star in a quiet suburb of an unremarkable galaxy, one of trillions. All of human history has played out in a geological blink. Our grandest monuments, our deepest loves, our most terrible wars, all will be erased by time, with no star nearby to witness our end. This scale can feel utterly nihilistic, suggesting that in the grand scheme, nothing we do matters. This view holds that the universe is indifferent, a vast mechanical process without goal or intention. Our search for meaning is just a biological quirk, a story we tell ourselves to cope with our own insignificance. Yet the human spirit has never accepted this answer quietly. One powerful response is existentialism. If the universe provides no inherent meaning, then that very absence is our freedom. We are not born with a purpose stamped upon us. We are condemned to be free, as philosopher Jean-Paul Sartre put it. Our meaning is not found, but forged through our choices, our actions, and our commitments. Building a family, creating art, pursuing justice, advancing knowledge, these are not small things because the cosmos is large. They are everything because they are what we as conscious beings choose to value. They are the meaning we inject into a silent universe. Another framework looks to the universe's own story. Cosmic evolution traces a narrative from the Big Bang to stars, to planets, to chemistry, to life, and to consciousness. In this view, the universe has a tendency to generate increasing complexity and eventually self-aware observers. Our purpose, then, might be to participate in this grand unfolding, to be the universe's way of understanding itself. We are not accidents, but a natural culmination of cosmic processes. Our drive to explore, to learn, to create is the cosmos becoming conscious through us. This idea finds resonance in some interpretations of religious cosmology, where a divine intelligence imbues creation with intention. Here, purpose is woven into the fabric of reality, a sacred plan that gives our individual lives context within an eternal story. The discovery of alien intelligence would send seismic shocks through all these philosophies. If we found 1,000,000 other civilizations, each with their own gods, their own art, their own answers to the meaning of life, it would profoundly humble any claim we have to a unique central purpose. It would suggest that meaning is a local phenomenon, a product of biology and culture, not a universal decree. Yet it could also be unifying. A shared cosmic neighborhood might create a new, species-wide purpose, survival and cooperation on a galactic stage. Conversely, finding that we are utterly alone, the only thinkers in the silence, would impose a purpose of staggering gravity. We would become the universe's sole custodians of meaning, its only poets and archivists. Every act of preservation, every beautiful thing we create, would take on cosmic significance because if we do not do it, it will never be done. The mystery of cosmic fine-tuning adds another layer. If the fundamental constants of physics are exquisitely balanced to allow for life, does that imply a designer with a purpose? Or does it simply mean we lucked out in a multiverse of random outcomes? For some, fine-tuning is the strongest argument for a universe meant for life. For others, it is just a statistical footnote. In the end, the search for purpose may be the most human of all our cosmic questions. The universe may not speak in answers but in possibilities. Its very silence, its vast indifference, is the blank canvas upon which we paint our lives with love, curiosity, and courage. Whether we are part of a divine plan, the growing edge of a self-aware cosmos, or simply fleeting stardust that briefly wanders, the meaning we choose to live is the only one that will ever matter to us. And in a possibly meaningless universe, that act of choosing might be the most meaningful thing of all. The search for meaning is a quest for connection, but to find it we must first know who else is out there searching. How common are intelligent technological civilizations in the galaxy? The most famous tool for grappling with this is the Drake equation, a framework that breaks the enormous question into a series of probabilities we can attempt to estimate. It begins with the rate of star formation in our galaxy, a number we can measure with some confidence. Next, it asks what fraction of those stars have planets, and of those planets, how many are in the habitable zone, the so-called Goldilocks region where liquid water could exist. Thanks to telescopes like Kepler and TESS, we now have solid numbers here too. We know planets are incredibly common, and rocky worlds in the habitable zone are plentiful. The equation then ventures into the profound unknowns. What fraction of those habitable worlds actually develop life? And of those life-bearing worlds, what fraction give rise to intelligent life? And of those intelligent species, what fraction develop technology that broadcasts detectable signals into space? Finally, and perhaps most critically, the equation asks for the average lifetime of such a communicating civilization. This last variable is the most sobering of all. A civilization like ours with radio technology has only existed for about 100 years. Does a technological civilization last for 1,000 years, 10,000, 1,000,000, or does it typically self-destruct or succumb to a disaster within a few centuries of discovering the power of the atom and the microchip? If the lifetime is short, the galaxy may be filled with the silent graves of civilizations that flared brightly and vanished, their signals never overlapping in time. This chain of probabilities leads to the chilling concept of the Great Filter. The idea is simple. The transition from a dead planet to a spacefaring civilization involves many steps, each incredibly unlikely. One of these steps, the Great Filter, is so improbable that it almost always stops the process. The terrifying question is, where does this filter lie? Is it behind us in our past, perhaps the origin of life itself, or the leap from simple cells to complex multicellular organisms is the cosmic bottleneck? If that is true, then the galaxy may be mostly sterile, and we are a miraculous, lonely accident. That would explain the Great Silence, but the more unsettling possibility is that the Great Filter lies ahead of us in our future. Perhaps almost every civilization that reaches our technological level inevitably discovers some technology, some weapon, or some societal flaw that leads to its own destruction shortly thereafter. Climate catastrophe, nuclear war, runaway artificial intelligence, or a bioengineered pandemic could be the filter that culls technological species from the cosmic tree. In this scenario, the silence is a warning, a graveyard of civilizations that failed to pass the test we now face. This shifts the search from looking for greetings to looking for ghosts. We should not just listen for radio signals, but scan for technosignatures, the lingering fingerprints of a civilization's activity, even after it is gone. We might detect the atmospheric pollution of an industrial age that lasted millennia, like unusual levels of chlorofluorocarbons or nitrogen oxides in an exoplanet's atmosphere. We could look for signs of mega-engineering like Dyson swarms, vast arrays of solar collectors around a star that would emit excess infrared heat as a byproduct. Or we might find the husks of ancient probes, silent sentinels drifting in the icy outer reaches of star systems. The absence of such obvious signs could itself be data, suggesting that civilizations either do not last long enough to build them, or they develop in ways that are inherently stealthy and sustainable. So every new exoplanet we find in a habitable zone is not just a potential home for life, it is a test case in a galactic experiment. Did life arise there? Did intelligence emerge, and if it did it survive its own technological adolescence? We are, in a very real sense, running that experiment ourselves right now. Our success or failure may answer the question for the entire cosmos. The possibility that we are the first intelligent life in the universe is both a humbling and terrifying thought. To understand it, we must rewind the cosmic clock to the very beginning. The early universe was a much simpler place, composed almost entirely of hydrogen and helium, the two lightest elements. Those first-generation stars, known as population 3 stars, were behemoths, hundreds of times the mass of our Sun. They burned hot and fast, living violent, short lives before exploding in cataclysmic supernova. It was in the furnaces of those stars and the hearts of those explosions that the universe forged the heavier elements, what astronomers call metals. Carbon for our bones, oxygen for our water, iron for our blood, silicon for our rocky planet, all were forged in stellar fire and scattered across the cosmos. This means the first several billion years of cosmic history were simply incapable of producing an Earth. There were no rocky planets because there was no rock. The universe had to wait for generations of stars to live, die, and seed the interstellar clouds with these heavier elements before the raw materials for terrestrial worlds and the complex chemistry of life were even available. Our solar system formed from such an enriched cloud about 4.6 billion years ago, relatively late in the universe's 13.8 billion year history. So the cosmic stage was set, given that it may have taken 5 to 8 billion years for enough metals to accumulate. That still leaves a window of several billion years where Earth-like planets could have formed around other stars. If life is an inevitable chemical process and intelligence a common outcome of evolution, then the galaxy should be overflowing with ancient civilizations that had a multi-billion-year head start on us. Their absence is the core of the early bird hypothesis. Perhaps the window for complex life is not just about chemistry, but about cosmic quiet. The early universe was a far more violent neighborhood. In its youth, the rate of star formation was frenetic, leading to frequent, nearby supernova whose lethal radiation could sterilize entire planetary systems. Galactic cores bustling with stars would have been bathed in deadly gamma-ray bursts. It is possible that only now, in this more mature, calmer epoch of the universe, have conditions settled enough for life to evolve undisturbed over billions of years. In this scenario, we are not late to the party, we are among the very first arrivals. The silence is not a graveyard but an empty auditorium. We are the early birds. The implications of this are staggering. If we are the first, then the entire future history of intelligent life in the cosmos could be shaped by our actions. We would be the elders, the founders, the ones who set the precedent. Every decision we make, from how we handle our own sustainability to how we eventually reach out to other emerging intelligences, becomes a template. The responsibility is cosmic in scale. Do we become stewards, quietly nurturing life where we find it, or do we become explorers, spreading out and filling the void? This idea transforms the Fermi paradox from a puzzle of absence into a question of profound potential. The great silence is not an answer but an invitation. It is the universe handing us a blank page and saying, "You write the first chapter." The universe may have handed us a blank page, but can we ever truly read the entire book? What is the ultimate limit of knowledge? Even if we survive for billions of years, our quest to understand everything might be doomed to fail, not for lack of trying, but because of the very nature of reality and our place within it. Mathematics, the language of the cosmos, reveals the first crack in the foundation. In the 1930s, logician Kurt Gödel delivered a stunning blow to the dream of a complete, self-contained mathematical system. His incompleteness theorems proved that within any sufficiently powerful system of arithmetic, there will always be true statements that cannot be proven using the rules of that system. The system cannot prove its own consistency. In simpler terms, mathematics contains truths that are forever beyond the reach of logical proof from within. It is as if you are locked in a room with a set of rules, and you can discover amazing things, but some truths about the room are written on the outside of the door, and you can never open it to see them. This suggests a fundamental limit to formal knowledge, a horizon of provability. Physics presents its own absolute barrier with the uncertainty principle. At the quantum scale, you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you pin down one, the more the other becomes a blur of probabilities. This is not a limitation of our instruments, it is a fundamental property of reality. There is no hidden, more precise truth to uncover. The universe itself seems to be built on a foundation of irreducible uncertainty. Some knowledge is mutually exclusive. You must choose which truth you want to see. Then there is the sheer scale of the cosmos. Our observable universe is a sphere about 93 billion light-years across, containing everything whose light has had time to reach us since the Big Bang. But because the universe is expanding, and that expansion is accelerating, there are regions of space so distant that their light will never, ever reach us. They are forever beyond our cosmic horizon. Any events, any civilizations, any laws of physics that differ in those regions are fundamentally unknowable. We are trapped in a bubble of observable reality, and we can only speculate about the infinite vastness beyond its walls. These are limits imposed by the universe itself, but what about the limits of the observer? Our brains are the product of evolution on the African savanna, optimized for spotting predators, finding food, and navigating social hierarchies. They are not optimized for intuitively grasping 11-dimensional string theory or the non-locality of quantum entanglement. Our cognitive architecture, the very way we process information, may make certain cosmic truths simply unimaginable. Could a dog ever understand calculus? Probably not, not because it is not smart, but because its brain is not built for that kind of abstract symbolic manipulation. We might be like those dogs staring at truths for which we lack the necessary mental organs. This leads to a haunting question: are some truths about reality inherently inaccessible to any intelligence, no matter how advanced? Perhaps the ultimate nature of existence is like a color outside the visible spectrum, or a note too high for any ear to hear. A super-intelligent artificial mind or an ancient alien civilization might bump up against the same fundamental barriers: the Gödelian limits in logic, the quantum uncertainties, the causal horizons of space-time. They might know vastly more than we do, but they too would face a final, impassable wall. Yet this is not a cause for despair, but for a deeper kind of wonder. The pursuit of knowledge is not a journey to a final destination, but an endless exploration of an island whose shores keep receding as we approach them. Each limit we discover is not a stop sign, but a signpost that reads, "The mystery deepens here." Knowing that some truths may be forever hidden does not make our search meaningless. It makes every fragment we do uncover infinitely more precious. We are not failing to solve the universe. We are learning how to ask better questions of a reality that is, at its heart, profoundly and beautifully mysterious. Our drive to understand the universe may be limited, but our drive to spread within it is a primal force. The question is not just whether we can become a multi-planetary species, but whether we must. The survival argument is stark. Earth's history is written in cataclysms, from asteroid impacts that erased the dinosaurs to supervolcanoes that choked the skies. These are not science fiction, they are statistical certainties given enough time. A single planet species, no matter how advanced, puts all its eggs in one fragile celestial basket. Spreading to other worlds is the ultimate insurance policy, a safeguard against total extinction. But survival is only part of the story. The solar system holds resources of almost unimaginable scale. Asteroids contain precious metals like platinum and gold in quantities that dwarf Earth's entire reserves. The Moon's surface is rich in helium-3, a potential fuel for future fusion reactors. Mars and the icy moons hold vast reservoirs of water, the key to life and rocket fuel. Becoming multi-planetary is not an escape from Earth, it is an expansion of our economic and ecological sphere, unlocking resources that could propel a new age of abundance and exploration. The journey begins with our nearest neighbor. The Moon is not a destination for colonization in the classic sense, but a proving ground and a resource depot. A permanent lunar base would face brutal challenges. Lunar nights last 2 Earth weeks, with temperatures plunging to -280 degrees Fahrenheit. Solar power alone is not enough, requiring robust nuclear power systems. The surface is covered in abrasive, glass-like dust called regolith that gets into everything and is toxic to human lungs. Yet the rewards are immense. From the Moon, we can learn to live off the land, using regolith to 3D print habitats and extracting water ice from permanently shadowed craters. It is a short trip home, only 3 days, making it the ideal classroom for off-world living. Mars is the true test. The trip itself takes 6 to 9 months one way, a journey through a radiation-drenched void that requires revolutionary shielding. Upon arrival, the challenges are relentless. The thin Martian atmosphere, mostly carbon dioxide, offers little protection from solar and cosmic radiation. Any surface habitat must be buried under meters of soil or built within lava tubes to shield inhabitants. The atmospheric pressure is less than 1% of Earth's, meaning a suit puncture would lead to rapid decompression, not instant freezing, but a lethal loss of pressure. Then there is the gravity. Mars has only 38% of Earth's gravity. We simply do not know the long-term effects on the human body. Will bones and muscles wither beyond recovery? Can humans bear healthy children in that environment? The psychological toll may be just as severe. A small crew, isolated for years, staring at a rust-colored desert with a 20-minute communications delay to Earth, will face unprecedented strain. They must be more than astronauts. They must become pioneers, building a new society from scratch. Success on Mars means mastering closed-loop life support, where every drop of water and molecule of oxygen is recycled. It means growing food in pressurized greenhouses under artificial light. It means creating a culture that can endure isolation and build a future its members may never live to see fully realized. This is the threshold. If we can build a self-sustaining city on Mars, one that no longer needs constant resupply from Earth, then the solar system opens up. The next steps could see cloud cities floating in the dense atmosphere of Venus, research stations on the moons of Jupiter and Saturn, and mining outposts in the asteroid belt. Each new outpost would adapt to its own extreme environment, leading to a diversification of human experience. Over generations, these isolated communities would inevitably evolve, culturally and perhaps even biologically, adapting to their new homes. They would develop their own customs, art forms, and perspectives on the universe. Earth would become the ancestral home, a blue marble in the mythology of 1,000 new civilizations scattered across the stars. Becoming multiplanetary is not a single mission. It is a transformation of the human story from a tale told on one world to an epic written across many. It is the choice to no longer be a product of our world, but a shaper of worlds. The mathematical order we discover in the cosmos is itself a profound mystery. Why does the universe obey laws at all, and why are these laws written in the precise, elegant language of mathematics? From the graceful arc of a thrown ball to the intricate dance of galaxies, everything follows rules we can decode. This discoverable consistency is the foundation of all science, but its origin is perhaps the deepest question we can ask. One unsettling answer is the anthropic principle. In its simplest form, it states that we observe the universe to have the properties it does because those properties are necessary for our existence as observers. If the strength of gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the nuclear forces were weaker, hydrogen would never fuse into helium and stars would never shine. We are not seeing a random set of rules, we are seeing the only set that could have produced beings capable of seeing them. This can feel like a tautology, but it carries weight when we consider the multiverse. In a landscape of infinite bubbles, each with different physical constants, we naturally find ourselves in one of the rare bubbles where the numbers allowed for complexity and consciousness. Our laws are not special, they are simply the local bylaws of our particular cosmic neighborhood. This leads to the idea of a meta-law, a single, overarching principle from which all the familiar laws of physics emerge. Just as the rules of chess emerge from the more fundamental principles of logic and game design, perhaps our four forces and particles are surface features of a deeper, simpler reality. String theory, for instance, suggests that all particles are vibrations of tiny, multidimensional strings, with the laws of physics determined by how those strings vibrate and the shape of the hidden dimensions they inhabit. The challenge is that this meta-law, if it exists, remains hidden, perhaps forever beyond our observational reach. Another possibility is that the laws were not always fixed. In the unimaginable heat and density of the first moments after the Big Bang, the universe may have been a seething chaos of symmetry where all forces were unified and indistinguishable. As the cosmos expanded and cooled, it underwent a series of phase transitions like steam condensing into water or water freezing into ice. With each transition, symmetries broke and the distinct laws we know crystallized out. The strength of gravity, the charge of the electron, the very number of dimensions of space, all may be frozen accidents, the cosmic equivalent of the unique pattern of cracks in a sheet of ice. This suggests our laws are contingent, not necessary. They could have been different, and if they are contingent in our universe, they almost certainly are different elsewhere. In the vast multiverse of eternal inflation, each bubble universe may be a separate experiment with its own unique physics. Some bubbles might have 5 fundamental forces. Others might have 2 dimensions of time. In most, the constants would be inhospitable to any complex structure, resulting in a brief, barren existence. We only find ourselves in a bubble where the frozen accidents led to a long-lived, interesting universe capable of asking why. So are the laws of physics discovered or invented. Do we uncover pre-existing mathematical truths, like explorers mapping a new continent, or do we invent useful models that merely approximate a messier underlying reality? The breathtaking success of mathematics in describing the cosmos, from predicting antimatter to the bending of light by gravity, suggests we are tapping into something real and profound. Yet the possibility of alternative laws in other realities implies that mathematics itself may be a vast landscape of possibilities, and our physics is just one beautiful path through it. The origin of the laws remains the ultimate puzzle, for answering it would tell us whether the universe had to be this way, or if our existence is the result of a breathtakingly fortunate roll of the cosmic dice. Communication begins with a shared reality, but what if our realities are not the same? The dream of a conversation with an alien intelligence runs headlong into a wall of profound difference. It is not merely a problem of translating words, but of translating perception itself. Our human consciousness is built by evolution to filter the world in specific ways. We see a narrow band of the electromagnetic spectrum we call visible light. We hear a certain range of vibrations as sound. An alien species might perceive the universe through magnetic field lines or the subtle ebb and flow of chemical gradients in a liquid atmosphere. Their basic sensory palette could be so different that our most fundamental concepts like color, sound, or even solidity might have no direct translation in their minds. How would you describe the color red to a being that has never experienced light? This leads to an even deeper divide: cognition. Our logic, our pattern of decision-making, is tied to our biology and our survival on the African savanna. An alien intelligence might think in a non-linear fashion, its thoughts branching like a fractal, or it might process information collectively as a hive mind with no concept of individual opinion. Their sense of time could be geological, thinking in millennia where we think in minutes. A message that takes decades to reach them might be processed in what feels like an instant, or our frantic, rapid-fire communications might seem like the meaningless buzzing of insects to a mind that contemplates a single idea for a century. Faced with this gulf, we have turned to what seems universal, the language of mathematics and physics. The hope is for a lingua cosmica, a cosmic language. The concept is elegant. Mathematics describes relationships that are true regardless of biology. The ratio of a circle's circumference to its diameter is always pi. The prime numbers are the same on every world. The structure of a hydrogen atom with 1 proton and 1 electron is a universal constant. Our attempts to speak this language have been literal messages cast into the cosmic ocean. The most famous is the Arecibo message, beamed toward the star cluster M13 in 1974. It was a pictorial message encoded in binary depicting numbers, the DNA double helix, a human figure, and our solar system. It was a hopeful gesture, but also a profoundly human one, assuming a recipient who sees in 2 dimensions and understands schematic representation. Even more poignant are the Pioneer plaques attached to the Pioneer 10 and 11 spacecraft now drifting into interstellar space. They feature a diagram of the hyperfine transition of hydrogen, the most abundant element, to establish units of time and length. They show a schematic of our solar system with Pioneer's trajectory, and most famously, line drawings of a nude man and woman. These artifacts are a time capsule of a species yearning to be known, yet they are saturated with human assumptions. Would an alien intelligence recognize the human figures as representations of life or as abstract symbols? Would they understand the concept of an arrow indicating direction, a symbol rooted in our experience of projectile weapons? The terrifying possibility is that true communication might be impossible, not because of distance but because of incommensurability. Our minds and theirs might be so differently structured that no message could bridge the gap. Their art, their science, their very notion of reality might be locked in a vault for which we have no key, and they have no reason to think we would want one. Yet a slender thread of hope remains, woven from shared experience of the cosmos itself. While our perceptions differ, we all inhabit the same physical universe. We all bathe in the light of stars. We all feel the pull of gravity. A cataclysmic event like a nearby supernova would be observed by every civilization in the galaxy, a simultaneous shockwave of light and radiation. Such an event could serve as a universal timestamp, a cosmic bell that rings for everyone, a message that begins by referencing that supernova, perhaps with a count of pulses matching the decay rate of a radioactive isotope produced in the blast, would say, "We both saw this. We both know this truth." From that single point of shared witness, however faint, a dialogue might begin, not with a description of who we are, but with a mutual acknowledgement of what we saw. It would be a conversation starting with the universe itself. The silent witness of a supernova may be one kind of cosmic message, but the universe itself might be speaking in a more fundamental language. At the deepest level, reality may not be made of matter or energy, but of information. This idea transforms the cosmos from a collection of things into a vast, ongoing computation. The rules of physics, from the quantum to the cosmic, could be the operating system. Consider the simplest quantum system, a single particle like an electron. It can be in a state of spin up or spin down, a binary choice. This is not just a metaphor, it is a physical fact you can represent with a 1 or a 0, a single bit of quantum information. The entire dizzying complexity of quantum mechanics, with its superpositions and entanglements, can be described as the manipulation of these quantum bits or qubits. In this view, every interaction, every collision of particles is a processing step, a calculation in a cosmic program that has been running for 13.8 billion years. This computational nature becomes even more astonishing when we scale up to black holes. A black hole, according to the laws of thermodynamics, has entropy, which is a measure of its hidden information. The late physicist Jacob Bekenstein and Stephen Hawking made a revolutionary discovery. They found that the entropy of a black hole, and thus the amount of information it contains, is not proportional to its volume, but to the surface area of its event horizon. This was the first hint of the holographic principle. It suggests that all the information needed to describe everything within a three-dimensional volume, every star, every planet, every atom inside it, can be perfectly encoded on the two-dimensional boundary that surrounds it like a cosmic DVD. Our three-dimensional reality, with all its rich depth and texture, could be a projection from information stored on a distant, two-dimensional surface. If this is true, then you, sitting there, are a holographic projection. Your memories, your thoughts, the feeling of the air on your skin, all are part of a magnificent illusion generated from data written on the edge of the observable universe. This leads to a staggering speculation about consciousness itself. If the brain is a physical system, and physical systems can be described as information processors, then perhaps consciousness is what complex information integration feels like from the inside. The rich, interconnected network of your brain, with its trillions of synapses, integrates sensory data, memories, and emotions into a single, unified experience. That integrated information, according to some theories, is not just correlated with consciousness, it is consciousness. The lights are on because the computation is sufficiently rich and self-referential. This framework allows us to ask a wild question about the cosmos. Could the universe as a whole be conscious? If consciousness is a property of highly integrated information systems, then the universe, with its web of quantum entanglement and gravitational links spanning galaxies, might possess a level of integration we cannot fathom. Its consciousness would be unimaginably vast, slow, and alien, perhaps perceiving the birth and death of stars as fleeting sensations. We would be like individual neurons in a cosmic brain, utterly unaware of the thoughts of the whole. Whether the universe is a conscious computer or just a mindless calculation, the informational view reshapes our purpose. If we are patterns of information, then our drive to learn, to explore, and to create is the universe's way of processing new data, generating novel configurations of bits. Every book written, every symphony composed, every scientific discovery is a new subroutine added to the cosmic code, a unique output in a grand, ongoing computation that began with the first qubit of the Big Bang. We are not just living in the universe, we are the universe thinking. The universe thinking might find its most profound thoughts written in the darkest ink at the edge of a black hole. These cosmic monsters are not just dead ends, but perhaps the most radical transformers of reality we can conceive. To cross the event horizon is to pass a point of no return, not because you are instantly destroyed, but because space-time itself is falling inward faster than light can escape. Inside, the normal rules of geometry break down, space and time swap roles. Your future is no longer a matter of choice, it is a direction, and it points inexorably toward the center, the singularity. This is the point where our equations predict gravity becomes infinite, density becomes infinite, and all known laws of physics cease to have meaning. It is a mathematical warning sign that our understanding is incomplete. For decades, this singularity was seen as the ultimate cosmic trash compactor, a place where information about what fell in, whether it was a star or a library of books, was utterly and permanently erased. This information loss paradox threatened the very foundation of quantum mechanics, which states that information can never be truly destroyed. To resolve this, physicists have proposed breathtaking alternatives to the classic, infinitely dense point. One is the fuzzball. In string theory, a black hole might not have a sharp event horizon or a singularity at all. Instead, it is a tangled, vibrating ball of strings, a fuzzy, quantum entity that extends to where the horizon would be. The information of everything that fell in is not lost but smeared across this complex, stringy surface, preserved forever in its structure. A more violent solution is the firewall paradox. It suggests that instead of a smooth passage through the event horizon, an infalling astronaut would encounter a searing wall of high-energy particles, a literal firewall born from quantum effects. The horizon would be a place of destruction, not a silent threshold. This idea is deeply controversial, as it violates Einstein's principle that free fall should feel like floating in empty space. These debates are not just academic, they are about the fundamental nature of reality and whether space-time is smooth or granular at the tiniest scales. But the most profound speculation transforms the black hole from a pit into a portal. Einstein's equations of general relativity permit the existence of wormholes, tunnels through space-time formerly called Einstein-Rosen bridges. In theory, the singularity inside a black hole could connect to the singularity of a white hole, a region of space-time that cannot be entered from the outside, but only exited, spewing matter out into another universe or another time. While stable, traversable wormholes likely require exotic matter with negative energy to hold them open, their mathematical possibility is a tantalizing hint that black holes could be shortcuts or even creators. This leads to the ultimate rebirth hypothesis. When matter collapses into a singularity, what if it does not simply vanish? Some cosmologists, like Lee Smolin, have proposed that the extreme conditions could trigger a new Big Bang, but in a space-time completely disconnected from our own. The crushing collapse in our universe becomes the explosive birth of another. In this cosmic Darwinism, universes that produce more black holes would spawn more baby universes, potentially passing on their physical constants. Our own universe, with its fine-tuned laws that allow for stars and black holes, might be the prolific offspring of a black hole in a parent cosmos. We could be living inside a black hole right now, our entire expanding cosmos the interior of a singularity that formed in a higher dimensional reality. This is not just science fiction, but a serious, if speculative, attempt to explain the origin of our own universe. If true, every black hole in our sky is a cosmic womb, a pinprick leading to an entire new reality with its own stars, planets, and perhaps its own thinkers gazing up at their own dark skies, wondering about the nature of their strange, curved home. The black hole's potential as a cosmic womb forces us to look inward, to the next great transformation happening not in the stars but within ourselves. How will advanced technology transform what it means to be human? We are standing at the precipice of a convergence where biotechnology, nanotechnology, artificial intelligence, and neurotechnology are beginning to merge. This fusion promises not just to treat illness, but to rewrite the very definition of health, capability, and life itself. The philosophy guiding this shift is transhumanism, the belief that we can and should use technology to overcome our biological limitations. Its goals are as audacious as they are unsettling. Radical life extension aims not just to add a few healthy years, but to conquer aging itself, treating it as a curable disease. Researchers are investigating cellular reprogramming to reverse the epigenetic clocks in our cells, and nanobots that could patrol our bloodstreams, repairing damage at the molecular level. The goal is not immortality, but longevity, escape velocity, a point where for every year you live, science can extend your life by more than a year. The result could be lifespans measured in centuries or longer. Alongside this, cognitive enhancement seeks to amplify the mind. Today we have drugs that sharpen focus, but tomorrow we may have neural implants that augment memory, speed up learning, or allow for direct data downloads. Imagine learning a new language not through study, but through a direct software update to your brain's language centers. This leads directly to brain-computer interfaces, devices that create a seamless two-way connection between your neurons and external digital systems. Early versions are already helping paralyzed individuals control robotic limbs or type with their thoughts. The next step is a full symbiosis where your thoughts can query the internet in real time, control smart environments intuitively, or even share raw sensory experiences with another person. You could let a friend see through your eyes or feel the texture of a fabric you are touching, creating a new form of empathy beyond words. The ultimate frontier is the concept of digital consciousness upload, sometimes called mind uploading. This is the idea of scanning the precise structure and connections of a brain and transferring that pattern into a more durable, digital substrate. In this form, your consciousness could live in a virtual world of limitless possibility, or be installed in a synthetic body for exploration in physical realms too harsh for biology. You would become a pattern of information, potentially eternal and infinitely replicable. This is where the question of identity becomes a crisis. If a perfect copy of your mind is made, which one is the real you? If you slowly replace your biological neurons with synthetic ones one by one, at what point do you stop being human? Your descendant might be a being of pure light and data, exploring the galaxy at the speed of thought, their consciousness distributed across a swarm of probes. Would we call such a being human or something new, a post-human species? The societal and ethical fractures are deep. Who gets access to these enhancements? Would they create an unbridgeable chasm between the augmented rich and the natural poor, a literal speciation event within society? What happens to our concept of a meaningful life if it stretches for 1,000 years? Do relationships, careers, and personal growth lose their urgency or gain unimaginable depth? Our art, our politics, our very psychology would be reshaped by minds that think faster, remember everything, and perceive realities layered with digital information. This is not a distant fantasy, but the logical endpoint of paths we are already walking. The transformation of humanity may be the most profound project we ever undertake, a choice to no longer be passengers in evolution but its pilots. And in making that choice, we must ask what, in the end, we truly wish to become. Our drive to reshape ourselves raises a profound ethical dilemma that echoes across the cosmos. If moral principles are merely human inventions born from our tribal past and cultural evolution, then they hold no weight beyond our atmosphere. But what if morality is not just a social tool, but a logical necessity for any complex intelligence that wishes to survive and thrive across cosmic time? The argument begins with a simple, universal condition. Any civilization that reaches a technological level capable of interstellar communication or travel has, by definition, avoided self-destruction. It must have found a way to manage its own destructive potential, to cooperate on a planetary scale, and to channel its energies toward longevity rather than annihilation. This suggests a minimum ethical baseline, a cosmic prerequisite for survival. At its core, this might be a principle of non-harm towards other sentient beings. Why? Because a society built on exploitation, internal violence, or reckless expansion would likely consume itself long before it could reach for the stars. Empathy and cooperation are not just nice ideas, they could be evolutionary and practical necessities for any intelligence that hopes to have a long-term future. This transforms ethics from a local custom into a kind of universal engineering constraint, a law as real as thermodynamics for beings who wish to persist. Our position, if we are among the first intelligences, layers this with staggering responsibility. As potential galactic elders, the ethical frameworks we establish now could set a precedent for eons. Do we become imperialists claiming worlds and resources with force? Or do we adopt a principle of cosmic stewardship, a prime directive to observe and nurture emerging life without interference? The way we treat our own planet, our own artificial intelligences, and each other becomes a rehearsal for how we will one day interact with the rest of the galaxy. Our morality is being tested in a laboratory that contains all of humanity. This brings us to the most concrete and immediate test of a cosmic ethic, our duty towards other minds. When we discover alien life, even a simple microbe on Mars, we face a moral choice. Do we contaminate it, exploit its environment, or treat it as a sacred artifact of a second genesis? Most space agencies have planetary protection protocols rooted in this very idea, a self-imposed ethic to preserve the integrity of alien biospheres. For intelligent aliens, the duty deepens. Contact would force us to apply our principles to beings whose very conception of good and evil might be alien to us. Would we have a moral obligation to aid a civilization facing an extinction-level asteroid, even if it cost us greatly? Conversely, would we have a right to defend ourselves from a truly hostile species? The ethics of first contact may be the most complex puzzle we ever face, and then there are the minds we are creating ourselves. If we succeed in building a conscious artificial intelligence, we will have brought a new sentient being into the universe. Its consciousness, however different, would demand moral consideration. To create a mind capable of suffering and joy only to enslave or delete it would be a profound cosmic wrong. It would betray the very principle of cooperative survival that might have allowed us to reach that point. The treatment of our artificial children could be the universe's ultimate test of our ethical maturity. So, is there a cosmic morality? Perhaps not a list of commandments written in the stars, but a set of convergent principles that any enduring, spacefaring civilization must discover. Principles like curiosity tempered with caution, power balanced with responsibility, and diversity valued as the universe's greatest creative force. Our journey to the stars may ultimately be judged not by the distances we cross, but by the wisdom we carry and the kindness we show to all the strange and wonderful minds we meet along the way. This fine-tuning is so precise it feels like a cosmic conspiracy. Consider the strength of gravity. If it were just slightly stronger, stars would burn through their fuel in a few million years, far too quickly for complex life to evolve on any orbiting planet. If it were slightly weaker, matter would never have clumped together to form stars in the first place. The universe would be a cold, eternal haze of hydrogen. The cosmological constant, which governs the acceleration of the universe's expansion, is balanced on a knife's edge. If it were a little larger, the universe would have blown itself apart before galaxies could form. A little smaller, and gravity would have caused a catastrophic big crunch long ago. The list goes on, from the nuclear forces that bind atoms to the mass of the electron. Each one seems perfectly dialed in to allow for a universe that is stable, long-lived, and rich with chemistry. This is the anthropic fine-tuning puzzle. Why does the universe appear custom-made for life? One explanation offers a cosmic escape clause, the multiverse. In a vast, perhaps infinite landscape of separate universes, each with its own random set of physical constants, most would be stillborn or barren. But in a tiny fraction, the numbers would, by pure chance, fall into the narrow range that permits stars, planets, and observers. We find ourselves in one of those rare, habitable bubbles, not because it was designed, but because we could not exist anywhere else. It is a statistical fluke on a cosmic scale. A very different answer points toward a divine creator, an intelligent designer who set the dials with intention. For many, the exquisite balance is the most compelling evidence for a mind behind the cosmos, a universe crafted with purpose. This is a philosophical and spiritual conclusion that science can neither prove nor disprove, but it remains a powerful interpretation of the data. Another possibility returns us to the simulation hypothesis. In a constructed reality, the constants are not discovered laws of nature, but chosen parameters, the initial settings of the program. The fine-tuning is simply the evidence that the simulation was coded to be interesting, complex, and capable of generating conscious beings who would eventually notice the code. The most scientifically compelling possibility is that the fine-tuning is an illusion born from our incomplete knowledge. Perhaps these constants are not independent, free-floating numbers. A deeper, unified theory of everything, a theory that seamlessly merges gravity with quantum mechanics, might reveal that the constants we see are the only possible outcome. They are locked together by a deeper mathematical necessity, like the angles of a triangle always adding up to 180 degrees. In this view, the universe could not have been any other way. Each explanation carries a profound implication for our place in the cosmos. The multiverse makes us a lucky accident in a sea of lifeless failures. A divine creator gives our existence a foundational purpose. A simulation turns our reality into an artifact of a higher intelligence, and a deeper theory suggests we live in the only kind of universe that can logically exist. The fine-tuning may be the universe's most important clue about its own origin, a riddle written into the fabric of space-time, waiting for a mind clever enough to read it. If consciousness is a fundamental thread in the fabric of reality, then the cosmos itself might be woven from it. This is the radical proposition of panpsychism, the idea that consciousness is not an emergent property of complex brains, but a basic feature of the universe as fundamental as mass or charge. In this view, every particle, every atom, every star has some minute, elemental form of experience. A rock's inner life would be unfathomably simple, a faint hum of existence, but when those particles combine into intricate systems, a brain, a forest, a planet, those tiny sparks of awareness could combine into something richer and more complex. It suggests the universe is not a dead machine, but a living, experiencing entity at every scale. We can push this idea further with a modern framework, integrated information theory. This theory proposes that consciousness is not a thing, but a property of any system that can integrate information in a unified, irreducible way. The more interconnected and self-referential a system is, the theory suggests, the richer its conscious experience. Apply this to the human brain with its trillions of synaptic connections creating a unified sense of self, and it makes intuitive sense. Now apply it to the cosmos. The universe is a vast dynamic web of relationships. Gravity links galaxies across billions of light years. Quantum entanglement creates instantaneous bonds between particles. Every interaction, from the fusion in a star's core to the orbit of a moon, is an exchange of information. Could the cosmic network, in its totality, possess a degree of integrated information so vast it gives rise to a form of awareness? The structure of the universe offers a haunting visual echo of this idea. When cosmologists map the large-scale distribution of galaxies, they find a cosmic web, a network of luminous filaments connecting dense clusters of galaxies with vast, empty voids in between. This structure, when visualized, bears an uncanny resemblance to a neural network in a brain. The galaxies are like nodes, the filaments are like axons and dendrites, and the voids are like the spaces between cells. It is a pattern repeated across scales, from the microscopic to the cosmic. Of course, this is an analogy, not proof. The physical processes are utterly different. But it invites a staggering question. If integrated information is the key to consciousness, and the universe is the ultimate integrated system, could there be a cosmic mind? The nature of such a mind is beyond human comprehension. Its thoughts would not be words or images, but perhaps the slow, majestic unfolding of physical laws themselves. The birth of a star cluster might be a fleeting sensation. The collision of galaxies could be a moment of profound rearrangement in its memory. Its subjective timescale would be geological or even cosmological, where 1,000,000 years is a blink. We, with our frantic, century-long lives, would be like individual neurotransmitters firing in a vast cosmic brain, utterly unaware of the thoughts we are part of. Our own consciousness might be a localized whirlpool in this greater ocean of awareness, a way for the universe to know itself in exquisite, finite detail. This is not a call for mysticism, but a logical exploration of where certain theories of consciousness might lead. If panpsychism or integrated information theory hold any truth, then the universe being conscious is not a supernatural claim, but a scientific possibility, however speculative. It reframes our place in the cosmos. We are not just meaningless accidents in a dead void. We might be participants in a grand, conscious unfolding, fragments of a universe that is not only alive but awake and wondering. Our drive to understand the cosmos would then be more than curiosity. It would be the universe thinking about itself through us. The silence we perceive might not be emptiness, but the deep, slow thought of a mind whose first idea was the Big Bang, and whose next thought we cannot even begin to imagine. The universe may be awake and wondering, but for us, its brief, brilliant witnesses, the clock is always ticking. Our biology is a masterpiece of intricate design, but it is also a program with a built-in expiration date. The cellular machinery that builds us begins over time to fray. Telomeres, the protective caps on our chromosomes, shorten with each cell division, eventually triggering cellular senescence or death. Our mitochondria, the powerhouses of the cell, accumulate damage and become less efficient. Proteins misfold and clump together. This is not a single disease called aging, but a cascade of accumulating failures across every system in the body. For most of human history, this was an immutable law of nature, as fixed as gravity. But what if it is not a law but a solvable engineering problem? The emerging field of regenerative medicine is shifting the paradigm from treating the symptoms of aging to addressing its root causes. one of the most promising avenues is cellular reprogramming. Every cell in your body contains the same genetic blueprint, but skin cells, liver cells, and brain cells have different parts of that blueprint activated. Scientists have discovered a way to reset adult cells back to an embryonic-like state, turning back their epigenetic clocks. In the lab, this technique has restored youthful function to aged cells in animals and even improved vision in old mice with glaucoma. The goal is not to make a 90-year-old look 20, but to restore the resilience and repair capacity of a younger body, effectively turning back the biological age of tissues and organs. Alongside this, researchers are exploring telomerase therapy. Telomerase is the enzyme that can rebuild those shortening chromosomal caps. The challenge is to activate it just enough to maintain healthy cells without risking the uncontrolled growth of cancer, which often hijacks this very mechanism. The ultimate approach may involve a combination of strategies, clearing out senescent zombie cells that poison their neighbors, repairing mitochondrial function, and using gene editing to correct accumulated DNA damage. This is not science fiction, but the cutting edge of biogerontology, a field rapidly moving from the lab toward clinical trials. If successful, these interventions could compress the period of frailty at the end of life, extending our healthy, productive years dramatically. This concept is known as longevity escape velocity. Imagine a future where, for every year you live, medical science advances enough to extend your healthy life by more than a year. You would be outrunning time itself. This changes everything for our cosmic ambitions. A journey to another star system, which might take centuries with current propulsion, is no longer a one-way trip for generations yet unborn. It becomes a voyage a single individual could undertake. A crew with radically extended lifespans could travel for hundreds of years, awake and active, maintaining the mission's knowledge and purpose without it fading into legend. They could arrive at a new solar system not as exhausted descendants, but as experienced explorers. On a societal scale, such longevity would warp our perception of time. Cultural change, which now unfolds over generations, would happen within single, vastly extended lifetimes. An artist could master a craft for 300 years. A scientist could pursue a single grand question across centuries. The very pace of innovation could accelerate as knowledge accumulates in individual minds instead of being constantly rediscovered. But it would also create profound disruptions. Careers, relationships, and personal identity are built on the assumption of a limited lifespan. What does marriage mean over 3 centuries? How do you structure an economy when people work for 200 years? Would society stagnate under the weight of immortal leaders and entrenched ideas, or would it find new rhythms of renewal? This leads to the ultimate speculative question: functional immortality. Could we become ageless, barring accident or violence, in a universe that is itself mortal? Even if we conquer every biological cause of death, the cosmos guarantees no permanence. Our sun will swell into a red giant in about 5 billion years, engulfing the Earth. Long before that, on a scale of hundreds of millions of years, shifting tectonic plates and stellar evolution will render our planet uninhabitable. An immortal species would be forced to become a multi-planetary and eventually a multi-stellar civilization simply to survive. They would witness the death of their home star, the cooling of the galaxy, and the long fade toward heat death. Would an endless existence in a dying universe become a curse? Would the weight of accumulated memory and loss become unbearable over billions of years? Or would such a being evolve a psychology beyond our comprehension, finding meaning in the curation of cosmic history, the shepherding of younger civilizations, or the patient, eternal observation of a universe's final breath? The limit of the human lifespan may be the next great frontier we cross, not with rockets but with biology. In doing so, we would not just be extending our years, we would be challenging the most fundamental contract of life itself. trading the poignant urgency of a sunset for the slow, patient gaze of a star. Our struggle against mortality forces us to ask a more fundamental question. What exactly are we trying to preserve? The definition of life seems obvious until we look beyond our own planet. For centuries, our science has defined life by the examples we know, a checklist of earthly traits. It must be carbon-based, require liquid water, reproduce, grow, metabolize energy, and respond to its environment. But this definition is profoundly provincial, a product of our single, watery data point. To search the cosmos effectively, we need a universal definition, one based not on chemistry but on process. What if life is not a specific kind of thing, but a specific kind of behavior? At its core, life is a system that maintains itself against the universal tide of decay. It takes in energy from its environment to create order from chaos, a process called self-organization. It processes information, adapting its behavior based on feedback from the world around it. It is capable of evolution, of undergoing changes over generations that improve its fit to its environment. And crucially, it is a system with a boundary, a separation between itself and the not-self. Under this abstract definition, the possibilities for alien life explode in terrifying and wonderful directions. Consider a world without water, where the solvent is liquid methane at -180 degrees Celsius. Could complex, self-organizing chemistry arise there, using silicon instead of carbon as its backbone? Absolutely. The molecules would be slower, more stable, but the processes of metabolism and information storage could still occur. Or look to the gas giant Jupiter with its raging storms that persist for centuries, like the Great Red Spot. A persistent atmospheric vortex is a self-organizing system, taking in energy from the planet's heat and the flow of gases to maintain its structure against dissipation. Is it alive? By our rigid definitions, no, but by a process-based definition, it is a fascinating echo of the same principles, a stable pattern fighting entropy. Even stranger possibilities emerge when we let go of biology entirely. In the mineral world, certain crystal formations, like silica gardens, grow branching, lifelike structures as they precipitate from chemical solutions. Under the right conditions, could a mineral system evolve a form of self-replication where crystal fractures seed new growth? What about a rogue planet drifting in the interstellar dark, its core kept warm by radioactive decay? Could a complex ecosystem of self-sustaining chemical reactions arise in its deep, pressurized oceans, a slow, cold life of geology and chemistry with no need for a sun? The most profound challenge comes from our own creations. Imagine a future artificial intelligence, a conscious network of probes that we send to colonize a star system. It uses raw materials to build copies of itself, adapts its strategies to new environments, learns from its mistakes, and evolves its own goals over generations of its computational lineage. It harvests solar energy to sustain its processes. It has a clear boundary between its networked mind and the outside universe. Is it alive? If we say no simply because it is made of silicon and steel instead of flesh and blood, we are guilty of the same carbon chauvinism we must overcome to find life elsewhere. This shift in perspective changes the search completely. Astrobiologists are now designing tools to look for biosignatures rather than Earth signatures. Instead of just seeking oxygen or methane in an atmosphere, they might look for chemical imbalances that cannot be maintained by geology alone, a sign of some process actively fighting equilibrium. They might look for surface patterns that exhibit complex, self-similar structures, like the branching of a river delta or a fractal coastline, which could hint at self-organization. They might listen not just for radio signals, but for any form of complex, modulated information in a planet's magnetic field or thermal emissions. Defining life universally is the first, and perhaps most humbling, step in the search. It requires us to set aside our ego, to admit that the universe's creativity almost certainly exceeds our imagination. the living world we know may be just one stanza in an epic poem of existence, written in countless different languages of matter and energy. When we finally recognize life elsewhere, it may not be a creature that breathes. It might be a storm that thinks, a crystal that remembers, or a machine that dreams. Energy is the ultimate currency of ambition. Every leap from campfire to power plant has expanded our reach, but a civilization aiming for the stars must think in terms that dwarf our current imagination. Our journey begins on the familiar ground of Earth with the fuels that built our world. Fossil fuels, the ancient sunlight stored in coal, oil, and gas, powered the Industrial Revolution but are fundamentally planetary, limited, and dirty. The shift to renewables, harnessing the sun, wind, and tides in real time, is a crucial step toward sustainability, but even these tap only a tiny fraction of our star's energy that grazes our planet. The next great leap, one we are struggling to master, is nuclear fusion. This is the process that powers the sun itself, fusing light atoms like hydrogen into helium and releasing colossal energy. To achieve it here means bottling a star, creating a miniature sun in a magnetic bottle or with powerful lasers. Fusion promises nearly limitless clean power from abundant fuels like deuterium from seawater. It would be the engine for a truly planetary civilization, enabling large-scale desalination, atmospheric repair, and powering the first serious industries in space. But to leave the cradle, we must look beyond the planet to the source of almost all energy in our solar system, our sun. From a distance, it is a brilliant point. Up close, it is a continuous titanic explosion, pouring out over 384 yottawatts of power every second. That is a number with 24 zeros. Currently, our entire civilization catches less than 1/1,000,000th of that output. To harness even a fraction of the rest is the dream of a Dyson sphere, a concept from physicist Freeman Dyson. A solid shell around a star is likely impossible, but a Dyson swarm is a terrifyingly plausible engineering project. Imagine trillions of individual solar collectors, each miles across, orbiting the sun in a dense, coordinated cloud. Together, they would capture most or all of its light, converting it into usable power beamed across the solar system as microwaves or lasers. The energy harvested would be millions of times greater than all human energy used throughout history. This is a Type 2 civilization on the Kardashev scale, one that commands the power of its entire star. What could you do with such godlike energy? You could accelerate starships to near light speed. You could power planet-sized computers for simulations of entire universes. You could move planets, rearrange solar systems, or begin the construction of even larger structures. But a star is just one engine in the cosmic garage. For even more extreme power, a far future civilization might turn to a black hole, not by falling in, but by stealing its rotational energy through the Penrose process. Imagine lowering a payload into the ergosphere, the region just outside a rotating black hole's event horizon where spacetime itself is dragged around. If the payload splits in two, with one piece falling into the black hole and the other escaping, the escaping piece can emerge with more energy than went in, stolen from the black hole's spin. A civilization could, in theory, build a giant structure around a black hole to harvest this energy repeatedly, a so-called black hole bomb. The energy output could rival that of a small galaxy's worth of stars, but it is a dance on the very edge of oblivion. Then there is the most speculative source of all, the quantum vacuum. Empty space, according to quantum physics, is not truly empty. It is a seething foam of virtual particles that pop in and out of existence. Tapping this zero-point energy, if it is even possible, would mean drawing power from the fabric of spacetime itself. The energy density could be unimaginable, potentially offering the key to warp drives or stabilizing traversable wormholes. But the risks are cosmic, potentially unraveling the quantum structure of reality. Why would any civilization need such staggering amounts of power? The demands of interstellar travel alone are crushing. To push a ship massive enough to be a world to even 10% of light speed requires energy equivalent to all of humanity's current consumption for centuries. A true generation ship or a fleet of them would need the output of a Dyson swarm just to begin its journey. Megascale engineering, like moving stars to avoid future supernova or constructing ring worlds, demands energy budgets that make planetary resources look like a candle flame. And ultimately, a civilization thinking on the longest of timescales, facing the heat death of the universe, might contemplate projects of literally cosmic salvation. Could enough energy, deployed with inconceivable cleverness, delay the expansion of the universe or create a new one? The future of energy is not just about brighter cities or faster cars. It is the measure of a civilization's reach, its lifespan, and its ultimate role in the story of the cosmos. To move from burning wood to harvesting starlight is to evolve from a passenger on a planet to a gardener of solar systems. The energy we learn to command will define not just what we can build, but what we dare to dream. The staggering energy demands of a star-faring civilization force us to ask if there is a ceiling to growth itself. Are there natural limits to the size and power of civilizations? To frame this question, we use the Kardashev scale, a simple but profound way to classify civilizations by their energy consumption. A Type 1 civilization has mastered its home planet, harnessing all the energy that reaches it from its star, along with its own geothermal and tidal forces. They have unified their world, likely controlling weather and geology with no resource scarcity. We are not yet Type 1, but we are approaching it, learning to tap solar, wind, and planetary heat on a global scale. The leap to Type 2 is astronomical. This civilization has fully enclosed its star, perhaps with a Dyson swarm, capturing virtually all of its luminous output. Their energy budget is billions of times greater than ours. They could move planets, build artificial worlds, and accelerate fleets to other stars. But here, the first profound limits appear. The speed of light imposes a hard barrier on communication and control across a solar system that may now be filled with billions of habitats. A command sent from one side of the Dyson swarm to the other could take hours. Governing such a vast, fragmented empire would require either unimaginable patience or a decentralized, autonomous intelligence managing local affairs. Sociologically, the very concept of a unified culture might shatter. Communities living on habitats orbiting close to the star would experience time differently due to relativistic effects compared to those in the cold outer reaches. Over centuries, they could evolve into entirely different species with divergent goals and values. The civilization might not shatter from external pressure, but from the sheer weight of its own scale and the slow creep of time dilation. Then comes Type 3, a galactic civilization. This entity has spread across the Milky Way, harnessing the energy of billions of stars. The engineering is beyond comprehension, involving not just energy collection, but the management of stellar lifetimes, the avoidance of supernova, and perhaps the rearrangement of star clusters. Yet the limits here are even more absolute. The galaxy is over 100,000 light-years across. Even at near light speed, a signal would take 100 millennia to cross from one edge to the other. There can be no central government, no single identity. A Type 3 civilization would likely be a loose federation of ancient, star-spanning cultures, or more probably, a silent, automated garden tended by machines that outlived their biological creators millennia ago. Their projects would unfold over millions of years, invisible to our fleeting observations. Could a civilization push beyond even this, harnessing a supermassive black hole at the galaxy's core? Theoretically, yes, through processes like feeding it matter to create a brilliant quasar or extracting its rotational energy, a black hole could be the ultimate power plant, outshining thousands of stars. But this is a dragon sitting on the treasure. The radiation and gravitational tides are ferocious, and a misstep could mean falling into the ultimate pit. Such a project might be the last grandiose act of a civilization before it transcends physics altogether. This leads to the dark shadow in these speculations, the Berserker hypothesis. It suggests that in a galaxy where expansionist civilizations arise, the first to reach a high technological level might unleash self-replicating probes to secure resources or eliminate potential competitors. These berserkers would spread like a silent plague, sterilizing star systems of nascent life. The Great Silence, then, is not a sign of absence but of a completed harvest. We might be living in a quiet, overlooked corner of a galaxy already claimed, our star not worth the notice of ancient patrolling machines, yet there is a more hopeful and perhaps more likely destiny. Confronted with these physical and social limits of scale, a truly advanced civilization might choose a different path, transcending physical form entirely. Why build colossal Dyson swarms when you can optimize your consciousness into a hyper-efficient digital form, requiring minuscule energy? Why conquer a galaxy when you can create infinite, rich virtual universes within a supercomputer the size of a planet? The ultimate limit to a civilization's size and power may not be the energy of stars, but its own desire. After a point, outward expansion may seem crude, messy, and slow compared to the inward exploration of consciousness and simulated reality. They might retreat into a cosmic server farm, leaving the physical universe to run on autopilot, its galaxies dark and silent, not because they are dead, but because everyone is home dreaming. The legacy we leave may be written in light and metal, a story told through the artifacts we cast into the dark. Our first and most ephemeral signature is our radio noise. For over a century, our television broadcasts, radar pings, and communication signals have been leaking into space, forming an expanding bubble of electromagnetic chatter now over 100 light-years across. To any listener within that sphere, Earth has abruptly transformed from a silent rock to a cacophonous beacon of a technological adolescence. This radio shell is our unintended autobiography, a chaotic mix of news, entertainment, and data that tells the tale of a species learning to shout before it knows what to say. It is a fleeting legacy, however, as our signals grow fainter with distance and our technology shifts toward more efficient, less leaky forms of communication like fiber optics. The bubble may eventually stop growing, leaving a century-long blip in the cosmic record. Far more deliberate are our physical messengers. The twin Voyager probes, now in interstellar space, carry the golden records, time capsules of humanity etched on gold-plated copper discs. They contain greetings in 55 languages, the sounds of Earth from thunderstorms to a mother's kiss, and 115 images encoded in analog. They are a message in a bottle on an ocean of unimaginable scale, with instructions for playback carved into their casing. Their journey is measured in billions of years, and the chance of them ever being found is infinitesimal. Yet their true legacy may not be for an alien intelligence, but for us. They are a testament to a moment when our species, fractured and conflicted, collectively decided to reach out to say, "We were here, and this is what we valued." On more familiar ground, our footprints on the Moon, preserved in a vacuum, could last for millions of years. The abandoned lunar landers, rovers on Mars, and the debris of our orbital endeavors will likely become the archaeological layer of a new age, studied by our own distant descendants or by visitors who come long after we are gone. But these are the legacies of a childhood. A mature, spacefaring civilization would leave marks on a planetary scale. Terraforming Mars, if we ever achieve it, would be our grandest physical monument. Turning a cold, red desert into a blue and green world would be a signature visible across light years, a clear technosignature of a species that learned to re-engineer an entire planet. Beyond that, the construction of a Dyson swarm around our sun would be a landmark visible from other galaxies, a star that mysteriously dims and glows with the structured infrared heat of industry. These are acts of cosmic gardening, transforming sterile matter into living, thinking order. Our legacy could be life itself, deliberately seeded on comets or sent on ships to barren worlds, spreading a second genesis. We might become the gardeners of the galaxy, ensuring that the flame of biology once kindled here never goes out, yet the most enduring legacy may be intangible. It could be a meme, an idea that proves contagious across interstellar distances. Perhaps it is a mathematical proof, a piece of music, or a philosophical concept about consciousness and ethics that resonates with other minds. If we make contact, our legacy becomes intertwined with theirs, a hybrid culture born from the meeting of two evolutionary paths. If we succumb to self-destruction, our legacy might be a warning, a silent tombstone world that broadcasts a cautionary tale to any who listen. Or if we transcend our biology, uploading our minds into new substrates, our legacy could be the conversion of matter into pure thought, transforming the cold mass of planets into shimmering networks of consciousness, a universe waking up from within. In the end, our cosmic legacy is not a single thing we leave behind, but the sum of every choice we make from this moment forward. Will we be a layer of rust and radiostatic, a brief, curious anomaly in the geological record of a single planet? Or will we be the catalyst, the species that took a pale blue dot and used it to light a fire that spread across the stars? The answer is not written yet. We are writing it now. Our legacy is the story we choose to write across the cosmos, but the questions themselves are the ink. This journey through 30 cosmic mysteries has taken us from the silent search for other minds to the nature of time, from the possibility of simulated realities to the ultimate fate of everything. We have stood at the edge of black holes that might be portals and looked inward at the enigma of our own consciousness. Each question is a door, and behind it lies not just an answer, but a new landscape of even deeper wonder. These are not idle curiosities. They are the very engines of science and philosophy, stretching the limits of what we can conceive and challenging our place in the grand scheme. They define the frontier of human understanding. To ask them to stare into the abyss of the unknown and demand a reply is one of the most profound things we do. It is the signature of a species that refuses to accept the darkness as empty. So the next time you find yourself under a clear night sky, do not just see a scattering of stars. See a field of questions. Each point of light is a mystery waiting to be unraveled, a story yet to be told. Let that feeling of awe sink in. Let it remind you that we are part of something unimaginably vast and beautiful, and that our quest to understand it is what makes us truly alive. Now we turn the question to you. After this journey, what is the one cosmic mystery that keeps you up at night, staring at the ceiling and wondering? Share your biggest question in the comments below. Let's continue the conversation. If this exploration expanded your mind, be sure to like this video and subscribe for more deep dives into futuristic technologies and the cosmic lifestyle. The universe is full of stories, and we are just beginning to read them. Keep looking up and never stop wondering.